Swayam Prabha. Digital India. Educated India.
Hi everybody, today I am continuing my lecture and let me first tell what I have covered in the last class and then the outlines of the today's lecture will be given to you. So, in the last lecture you have learned the theory of bending in thin plates and what are the assumptions related to bending, expression of strain in terms of vertical displacement we have obtained, then effect of multiple middle surface stretching that we have obtained, expression of moments in terms of vertical displacement, principal moments on any inclined plane, equilibrium equations of for thin plate. So, that was our last item covered in the last class, and you remember that I have arrived a fourth order partial differential equation with a biharmonic operator. The equation has some speciality in mathematical physics, and you know that this type of equation also represents the Airy stress function equation. So, we shall now proceed how to solve this type of this equation for different boundary conditions of the plate and what are the general method available and whether the method yield the exact solution or we require to adopt any approximate method, that will be discussed in our class. Okay. So, discussion on governing differential equation, first I will cover what are the available methods or techniques for the solution. Especially today I will discuss about the exact solution. Approximate solution will be covered later in separate classes. Then boundary conditions in the plate, because plate has straight edge or it may have curved boundary also. So, today I will specially discuss the boundary condition for straight edges. Later on I will go to the boundary condition for the curved edge. Then there are some cases where the closed form solution is readily obtained. Very simple function is chosen and that function is seen to satisfy the boundary condition as well as your differential equation. So, nobody can deny that this function is not a correct solution, it will yield a exact solution for that, but there are some specific boundary condition and specific loading for which only this is possible. So, one of the rare cases of exact solution of plate that there are some examples. Today I will cover the circular plate with clamp boundary. For that you can readily obtain the exact solution choosing a simple function. Then I will discuss the pure bending of plate when the plate is subjected to pure bending moment along the edges, how it deforms, that I want to cover, and pure torsion of the plate. Okay. Now, if you see the nature of the differential equation, del 4 is the biharmonic operator, and if the right hand side of this equation is 0, then in mathematical physics it is known as biharmonic equation. So, the homogeneous solution for that type of biharmonic equation is already in existence in different theories of mathematical physics, and here if we go for the plate subjected to a loading, transverse loading, or it may be some edge loading also where the homogeneous part has to be solved imposing the boundary condition at the edges. So, that condition may also arise. So, differential equation of the plate must be satisfied by the solution and the solution must satisfy the boundary condition. If two conditions are satisfied simultaneously, then we call the solution as exact solution. Okay. Now, we will focus on the exact solution in this class specially. Later on, some approximate method where exact solutions are not possible will be covered. Okay. So, let us see the general techniques that are used for the exact solution or solution of the plate problem are closed form solution that satisfy the boundary condition as well as differential equation. Then solution of biharmonic equation, that is you get an homogeneous solution and over which the particular solution due to forcing term has to be superimposed, then only you will get the total solution or complete solution for a linear case. So, for a linear case, homogeneous solution plus particular integral due to forcing function will give you the complete solution. So, that case may also arise. Now, in certain cases the trigonometric series provide very useful tool or very useful way of finding the exact solution of the plate problem for specific boundary conditions or for specific loading. Especially for some specific boundary condition, single trigonometric series or double trigonometric series can be conveniently used to find the closed form solution. Okay. The rigorous solution of the plate is essentially a boundary value problem, because boundary condition you have to impose. When you find the homogeneous solution of the biharmonic equation, then you will get, because it is a fourth order equation. So, imposing the boundary condition at the two edges, you will get the 4 constants or 4 equations that has to be solved simultaneously, and you will get the problem that constant, finding the constant of integration is a problem. In many cases, to simplify this, we adopt the symmetric loading, antisymmetric loading. So many techniques are used to simplify the calculation of the constants of integration, because it sometimes involves a lengthy calculation. Okay. So, closed form solution of the plate problems are limited, that statement I am making here, and it is true. In many cases you will not get, then you have to adopt a numerical techniques, either finite difference or finite element techniques or any other numerical techniques, solving the differential equation, integrating the equations, you can use any numerical methods. So, here WH is the homogeneous solution of the homogeneous solution of the plate equation, that means a biharmonic equation, and WP is the solution for the forcing function that I call as a particular integral or particular solution. Okay. Now, let us see the boundary condition, because I told you that boundary conditions are the important components of the plate problem. When the boundary conditions are satisfied, then you will get the solution which is close to the exact value. Okay. So, boundary condition, again there are 2 types of boundary condition. One is your geometric boundary condition and another I can term it as a force boundary condition. In the geometric boundary condition, the deflection and slopes are the parameter that have to be known at the edges, and for force boundary condition, the shearing force and twisting moment or bending moment have to be known at the edges. Okay. Now, here I take an example of a rectangular plate which has straight edges. So, the rectangular plate is say OA BC, that you are seeing here, the rectangular plate. The length of the plate is A, which is along the x axis, and width of the plate is B along the y axis. Okay. And you can see here that edge OA is fixed, it is clamped, and edge AB is also fixed. For example, we have a steel plate at one edge along the edge throughout continuously it is welded to another plate or another say element of steel. For example, base plate is welded, okay, or flange is welded to the web. So, this condition may occur. So, that means it has a welded edge OA which represents the fixed boundary condition. Similarly, AB is also an edge which is welded. So, it represents a fixed boundary condition or clamp boundary condition. Now, the boundary condition OA, I will specify that you see along OA this y is 0. So, along OA y is 0, y value is 0 if I refer O as the origin. If I refer O as the origin, then along OA y is 0. So, that means deflection is 0 along OA because it is fixed. So, W at y is equal to 0 is one condition that have to be imposed here. Then slope along the y direction. So, since this is fixed, so the slope along the y direction, the deflection curve will be such that the tangent here will be almost horizontal if the plate is horizontal. So, the tangent will have 0 angle making with the horizontal plane. Therefore, the slope is 0 at the fixed edges, hence del W del y at y is equal to 0 equal to 0. So, del W del y, that is partial derivative of del y deflection is taken, because deflection is a function of two variables x and y. Okay. Again you see at the edge AB. So, you have to identify what is the edge. At the edge AB, x is A, okay. X is A, and this AB is parallel to y axis. Okay. So, the AB length is the any y coordinate on AB will vary from 0 to B, okay. But x is fixed, x is A along the AB. So, at x is equal to A, again you are getting the deflection at x equal to A is equal to 0. So, whatever deflection solution you obtain involving the 4 constants of integration, then you can impose this condition at x is equal to A to relate the constant with their 0 value. Okay. Then since this is AB is fixed along the y direction, so the slope of the deflected curve along x axis, along x direction will be 0, because tangent will be making 0 angle with the x axis at the fixed edges. So, therefore, we have taken the partial derivative of W with respect to x is 0, substituted the value of x is equal to A. Okay. So, this is one important condition that we generally encounter in our practical situation or practical life, that is the clamped edges. Okay. Next, let us go to simply supported edges. That is very common condition, and it is mostly useful in simplifying the work, because simply supported condition, although in the previous case you have seen that deflection and single derivative of the deflection is taken, but simply supported, although it is a very simple condition, but the higher derivative is required. So, I will now discuss what is simply supported condition. So, simply supported conditions are here in the drawing. It is seen that OA is also simply supported, OC is also simply supported, and BC is also simply supported. That means, x is equal to 0 is simply supported, x is equal to 0 is your OC. So, OC edge is simply supported. Then y is equal to 0, that means the edge OA is also simply supported, and then y is equal to B, that is the side CB or BC is also simply supported. So, let us see what are the conditions that to be written for simply supported edges. In a simply supported edges, we know that deflection and bending moment has to be 0. So, rotation is allowed in this simple support that we know. So, W is 0, there is the deflection at y is equal to 0 for the edge OA. I am writing the condition for edge OA first. Okay. So, if I write the condition for OA first, y is 0. So, therefore, W at y is equal to 0 Okay. That is the one condition. Then second condition, bending moment along y direction. Since this is simply supported along the y axis, so slope at x y is equal to a along y axis cannot vanish. So, therefore, the bending moment curvature exists and therefore, bending moment is 0. So, rotation is allowed. So, moment is 0. Okay. So, bending moment expression we know that minus d bracket del square w del y square, that is the curvature in y direction, plus mu, that is the Poisson ratio, into curvature in x direction del square w del x square equal to 0. Now, you can see this edge OA is simply supported. So, there cannot be any curvature along the x direction, it is simply supported along the x axis. So, there cannot be any curvature or slope along the x axis, along the edges. So, naturally, we take this dw del square w del x square equal to 0. Hence, the condition second condition is simplified as only as the equation this del square w del by del x square equal to 0. So, second derivative of w with respect to x square equal to 0. So, this is the condition at y is equal to 0. So, two condition we got at y is equal to 0. Now, if I want to write the condition for the edge OC, then how will write? OC is the x is equal to 0, okay, x is equal to 0. So, boundary condition at OC will be w is equal to 0, that is one condition, and second condition will be the bending moment along the x direction is 0. So, bending moment along the x direction is minus d del square w del x square plus mu del square w del y square. But since it is supported along the y axis, okay, along the edge OC which is parallel to y axis. So, there cannot be curvature along the y direction. So, that means del square w del y square is 0. So, for that edges the condition will be w at x is equal to 0 is 0 and del square w del x square at x is equal to 0 is 0. So, it can be written in the similar way, okay, at this edge OC, all right. Now, let us go to other condition. That condition I have written along OC, okay, that I have told you. Now, it is written and you will get in my note also. So, free edge, let us see what the free edge indicates. Free edge, though there is not any support, but condition imposed is very complex at the free edge, because at the free edge we know that forces or stresses vanishes. Okay. So, therefore, the force boundary condition have to be imposed on the free edges, not geometric boundary condition, because at the free edge both slope and deflection cannot be 0. In the simply supported edges, we imposed one geometric condition, that is w is equal to 0, but one force boundary condition, that bending moment is equal to 0. In clamped edges, we imposed two geometric conditions only, that w is equal to 0 and slope is equal to 0. Simply supported edges, one geometric condition and one force condition, but in the free edges geometric condition cannot vanish, because w has to be non-zero and slope also has to be non-zero. So, in that case we have to impose the force boundary condition, that is condition for shearing force and bending moment. Now, in the plate you know that due to generation of shear stress, okay, there will be twisting moment. So, at the free edge we have three quantities to be vanished. One is bending moment 0, twisting moment 0 and shear force 0. Now, since this edge AB is located by x coordinate as x is equal to a. X is equal to a denotes the edge a b completely. This along a b the y coordinate varies from 0 to b, but x coordinate is fixed, x is equal to a along a b. Okay. Now, here three conditions are there. These three conditions have been given by Poisson, and later on this other authors Kelvin and Tate found that three conditions are not necessary, because this last two conditions can be combined, that is the shear force and twisting moment can be combined to give a single condition, because these are not independent quantities. Okay. So, Kelvin and Tate pointed out that second and third equation that I have shown you, that for bending moment and the twisting moment and shear force 0 can be combined, because they are not independent, and if you combine it you will get a realistic boundary condition. Okay. Now, let us see how we can combine it. In the adjacent figure we see that the twisting moment mxy acting on a element dy, because all quantities in the plate are this quantities per unit width, okay, that you remember. All quantities in the plate are this whatever quantity stress resultant, these are per unit width. So, mxy is also per unit width. So, if it acts on a length dy, so total twisting moment on this length will be mxy dy. Okay. Now, you can see this twisting moment mx dy can be represented by two equal and opposite forces mxy and mxy, so that it give rise to a couple mxy dy. Okay. So, this mxy dy is equivalent to a total mxy and dxy equal and opposite forces is equivalent to a couple mxy dy. Okay. So, based on that it is found that in adjacent element there will be some increment mxy plus dmxy. dmxy is the increment which in the full form is dmxy by dy into dy. Okay. That is coming from Taylor series expansion that I have given you in the equilibrium of equation lecture. Okay. So, how the incremental quantity is written on the opposite faces or at a distance given by at a distance dx or dy apart. Okay. So, this on the adjacent element you will get that mx plus dmxy, this is the twisting moment. So, Kelvin and Tate pointed out that any free edge addition of vertical shear is already there. So, in this edge the vertical shear qx is already there. If qx is added to the shear force generated due to twisting moment, and then it is equated to the S shear, if there is some S shear, then it will represent the true boundary condition. Okay. So, at the free edge there is no shear force. So, S shear is 0. So, that means the S shear that is to be balanced by the component of shear force acting on this edge qx plus the increment of shear force due to twisting moment. Okay, twisting moment. So, let us see how this can be found out. So, Kirchhoff has given an expression for the S shear, therefore, it is popularly known as Kirchhoff S shear. So, in this slide you can see that net vertical force in the element of dy, you will find dmxy dy into dy. Okay. So, you can see this is the unit of force equivalent to the unit of force, because mxy is the force per unit length and this is your this y. So, this will be again the unit of force per unit length, because the shear force is expressed as the unit of force per unit length. Okay. Hence, total vertical shear at the edge should be, now total vertical shear say Vx is another quantity which is total vertical shear. So, Vx multiplied by the length of the edge which is dy or length of the element dy should be equal to the shear force that is generated due to vertical force qx into dy for this element plus this is the component of shear force produced by twisting moment. So, if these two forces are added and equated to the S shear, then it will reflect the true boundary condition at the free edge. So, Kirchhoff has given this expression and dividing both sides by dy, you will get V x is equal to q x plus d m x y by dy. So, this is the S shear force, S shear force. Now, at the free edge, since there is no shear force acting, so S shear is 0. So, V x will be 0 at the fixed end. Now, let us find out what is the expression for V x in terms of deflection, because we will solve the equation of deflection. Plate equation is expressed in terms of deflection, the generic equation. So, we will find the solution in terms of deflection, which is a function of x y, x and y. So, therefore, let us express the S shear in terms of deflection. Now, here you can see that q x from the equilibrium equation, if you remember in my last class, we have obtained the equilibrium equation that q x equal to del m x by del x plus del m y x by del y. Okay. So, what is m x? M x is the bending moment in the x direction, and bending moment in the x direction is given as minus d del by del x del square w del x square plus mu del square w by del y square. This is the bending moment expression along the x direction. So, the first derivative of bending moment is taken and then the first derivative of twisting moment is taken. Okay. So, with the twisting moment expression, that is the twisting curvature del square w by del x del y. With the twisting moment, you know that a term d into 1 minus nu is associated. So, this term is there again and it is minus. So, minus d 1 minus nu is there and the derivative of the twisting curvature is taken with respect to y. Okay. Now, if you take this differentiation, then you will find that cubic the third derivative will be resulting, and after simplification it is a very interesting thing that after simplification in the S shear expression, in the shear force expression, you will not get any Poisson ratio term. So, there is no Poisson ratio term in the shear force expression, shear force due to vertical force or transverse force. So, shear force due to transverse force, transverse load in the plate is simply minus d del by del x, and this you know, this is the Laplacian equation. So, we can now say that q x is nothing but minus d del by del x into del square, this is the Laplacian operator into w, and here for q y the derivative has to be taken with respect to y. So, once we know the expression for q x, now substitute the expression for q x here from here to here. Okay. I brought here this to here, okay. And d m x y, you know that the expression for d m x y is this term and multiplied by this term. So, I have brought this expression for d m x y and I differentiated this with respect to y. Okay. So, after differentiation and rearranging, you will find that S shear is giving a very interesting expression, that is S shear is equal to minus d third derivative of w with respect to x plus 2 minus nu third derivative of w with respect to dx del y square. Now, you can see here this is the S shear force at x is equal to a, that is at the x edge, means x coordinate is constant along the edges. Okay. X coordinate is constant, but y is varying. If for example, we want to find out, say in the previous case, let me show the figure. Say this is the free edge that I have taken a b where the x coordinate is constant, x is equal to a. For example, if OA is free instead of clamped edge, suppose OA is free, then we have to write at y is equal to 0, okay, y is equal to 0, S shear V y is 0. So, expression for V y can be written with an analogy of that expression. V y will be minus d del cube w del y cube plus 2 minus mu del cube w del y del x square. Okay. So, for depending on the edge, okay, what the coordinates are specified, you can express the S shear, and S shear has to be equated to 0 at the free edge, that is the first condition. Second condition, at the free edge there will not be any bending moment. Okay. So, bending moment, because this is the x edge, so x is equal to a, bending moment is 0. So, bending moment expression is 0, but here in the simply supported edge compare the two expression. Here for free edge we are equating bending moment 0. In the simply supported edge we also equated bending moment equal to 0, but you can see the distinction or difference between these two expression. In the simply supported case, where the bending moment at x is equal to a, that edge was simply supported, we take it to 0 and then we neglected the curvature along the y direction. Okay. So, only del square w del x square was there, but here interestingly you can see, because it is the free edge. So, curvature cannot vanish. So, it is going to be deflected and free edge deflection will be measurable, significant deflection will be there at the free edge, slope will be there. So, therefore, you have to take two terms in the moment expression, and B x is known as the Kirchhoff's S shear. Okay. So, that is very important condition for the free edge, because originally Poisson has given three conditions: the bending moment 0, twisting moment 0, S shear 0, but twisting moment and vertical shear are combined to give a Kirchhoff S shear. So, ultimately the final condition becomes reduced to 2, from 3 to 2. So, it becomes easier after combining these two expression, twisting moment and this vertical shear force. Okay. Now, let us go to the other condition, that is sometimes we get this type of situation, a plate or slab, say for example, a slab is supported by a beam, where beam is also a elastic element. Okay. Because when the slab load is transferred to the beam, beam has to react to this load. Okay. Beam is not a rigid element. So, when the load is applied to a elastic element or a flexible element, it has to undergo some displacement, whatever small may be. So, similarly here, due to load transfer from the slab to the beam, there will be some deflection in the beam, nobody can deny, and you can also see that this edge where it is supported by the beam, elastic beam, the moment that the bending moment that acts along the direction, that is along the lengthwise direction here, we will also try to rotate the beam. Okay. So, this bending moment has to be resisted by the beam torsional capacity. Okay. So, you are understanding here that two conditions are necessary. One is that the beam deflection here will be same as the plate deflection, but beam deflection will only can be found when we know the distributed load over the beam. Distributed load over the beam is nothing but the S shear along this edge. Okay. Whatever S shear you are finding along this edge, this will be the load acting on the beam. Similarly, the bending moment whatever you get here for the plate, this will be your distributed twisting moment over the beam, which has to be resisted by the torsional moment or torque in the beam. Okay. So, let us find the mathematical expression for these conditions. Okay. So, two conditions I have expressed and I have written here. We should know two parameters for the beam. one is B, that is the flexural rigidity of the beam, E is the modulus of elasticity of the beam, and I is the moment of inertia of the beam. It is not necessary that plate and beam should have same modulus of elasticity. Beam may be of different materials. Suppose if you construct a slab say of concrete of say 20 MPa, then beam may be of concrete of 30 MPa. Okay. So, there will be difference of modulus of elasticity. Again, two different types of metal can also be used when the metallic plate is resting on another metallic support. So, therefore, this modulus of elasticity of the beam not necessarily be same as the modulus of elasticity of the plate. So, that you should remember. Then the torsional rigidity of the beam. Torsional rigidity is defined as the product of shear modulus into torsional constant J. Okay. Torsional constant J is slightly difficult to find out, especially for rectangular section, because you will find that a rigorous solution is obtained for the torsional constant, and a chart was given in the book of Theory of Elasticity by Timoshenko for rectangular beam for of different this width depth ratio. Okay. So, that you will find. So, coefficients are given and you can find from that coefficient. For a circular section, the torsional constant is very easy. For circular section, J is nothing but polar moment of inertia, but for rectangular section or other thin wall section, the torsional constant is not readily determined as the sum of the moment of inertia, that is not equal to the polar moment of inertia. Polar moment of inertia is nothing but I x plus I y. Okay. That is I x plus I y gives a moment of inertia perpendicular to the x and y axis, but it is not the case of other type of section. Only it is true for circular section, where you can easily get the polar moment of inertia as I x plus I y. However, for rectangular beam or rectangular support, that rectangular sectional support that we are showing here, the torsional constant has to be found out by proper method. Okay. So, these are two parameters that should be known for beam, then only we can write the boundary condition. Okay. So, for the beam, if we see the deflection of the beam is to be written as a fourth order equation E I del 4 W del y 4, that is the differential equation or the very well known equation for beam deflection subjected to uniformly distributed load of constant cross section B. Then you can see the right hand side is nothing but the load transmitted on the beam, and load transmitted on the beam is nothing but the S shear. You can see this quantity is S shear, there is the S shear per unit length will be distributed load on the beam. So, knowing this quantity at x is equal to A, we can find out or we can impose the boundary condition to evaluate the unknown constants of integration. So, this indicates that deflection of the plate at edge x is equal to A will be equal to the deflection of the beam. Okay. Then second boundary condition is obtained from the twist of the beam produced due to edge moment x mx. So, at the edge x there will be the bending moment mx along the x direction, and you can see the resisting moment is offered by the beam due to its torsional rigidity. Okay. So, this moment has to be found. Bending moment expression we already know it. So, bending moment expression is known here, and we have equated this to torsional moment or torque of the beam, how it is evaluated. For example, at one end of the beam or at one element of the beam, the couple is empty, torsional couple is empty. At a distance dy, the torsional couple will be empty plus d empty dy into dy, okay, at a distance dy. So, that means, if I take the equilibrium of the element for torsional moment, because at the other side the sign will be different. So, this minus this will be your bending moment mx dy. Okay. So, you can see that this quantity the first line equation is nothing but dmt dy is equal to mx at x is equal to a. That means, here the torsional moment, that is you have to find out, and torsional moment is nothing but, what is the torsional moment in a beam? Torsional moment of a beam, if we know the twist, rate of twist, okay. Rate of twist multiplied by the torsional rigidity is your torsional moment. So, rate of twist is nothing but del square w del x del y, and it is multiplied by the torsional rigidity C, which is nothing but equal to G j. G is the shear modulus of elasticity, and its derivative is taken with respect to y, and it is equated to the bending moment at x is equal to a. So, both the quantities are evaluated at x is equal to a. So, this gives the second boundary condition for this case, when the plate is supported along the elastic beam, okay, continuous support, there is no discontinuity of the support, that you should remember. So, MTA is found from the rate of change of angle of rotation at any cross section multiplied by the torsional rigidity. So, after simplifying, you will get this. This is the equation, second equation for the boundary condition of this case, when the beam is plate is resting on the elastic beam, okay, and the first boundary condition is this. Okay. So, two boundary condition we have written, all right. Now, there may be case when one of the edge is supported by the linear spring continuously distributed, there is no break, although in the figure you can see that a break is there, but it is very with a very close spacing. So, it is a distributed spring, okay. It is acting on this plate edge. If this is the origin of the coordinate system, then x is equal to a, this spring is distributed or spring is attached at edge x is equal to a. So, this is linear spring. Another case may be there when the torsional spring or rotational spring is attached at this edge x is equal to a. So, these are the two non-classical boundary conditions. Previous one also non-classical boundary condition. Classical boundary conditions are clamped, pinned or simply supported, and your free, clamped, simply supported, free. These three are classical boundary condition. Non-classical boundary condition, I have shown that the beam resting on the elastic support, okay. Then plate resting on the elastic beam, then your this plate resting on the linear spring, plate resting on the rotational spring. So, let us see what may be the equation for boundary conditions in these two cases separately. So, first let us see S supported by linear spring. So, linear spring is supported. So, two conditions we have to impose, bending moment at edge x is equal to a is 0, here bending moment is 0, and spring force here due to deflection at the edges, spring will offer resistance. So, spring resistance at this edge is k, stiffness of the spring multiplied by the deflection, this should be equal to your S shear. Okay. So, spring force should be equal to S shear. So, that is one condition, but first condition is bending moment equal to 0. So, bending moment equal to 0 gives this simple equation del square w del x square plus mu into del square w del y square equal to 0. This is the bending moment expression at x is equal to a, you have to substitute in the expression x is equal to a, then only you can write the equation. And the second condition, spring force equal to S shear. So, this is the S shear expression at x is equal to a, that we have derived earlier, plus k w, that is the spring force equal to 0. That means, you can write the d into this whatever quantity is there within the second bracket equal to k w. So, it indicates that spring force has to be resisted or has to be balanced by the S shear. So, these are the condition when the one edge is supported by linear spring. Okay. Then S supported by the rotational spring, two condition at the edge x a must be satisfied. What are the condition? Let us see. Since it is rotated by the rotational spring or torsional spring, it will offer resistance to your this bending moment along the edge. So, that means, along the edge the bending moment transferred on this from the plate should be balanced by the resisting moment offered by the rotational spring. Okay. So, that is one thing, the bending moment along the edge x is equal to a is equal to the resistance or resisting torque offered by the rotational spring, and second condition is S shear is 0. Okay. So, hence we can write two equations at the edges. One is this is your bending moment, okay. This is your bending moment plus this is the rotational or torsional resistance offered by the spring. Beta is the torsional constant or rotational spring constant that we take. Beta is the rotational spring constant multiplied by the angle of rotation dw by dx. So, this should be equated at x is equal to a for such cases to get first condition of boundary. Second condition of boundary is obtained by equating S shear equal to 0. So, we have discussed boundary condition that we generally encounter in practice, classical type and non-classical type. Okay. In classical types are common, but non-classical types also we have to impose in certain cases. All right. Now, I want to discuss that in certain cases of plate problem, we can obtain a very interesting solution without a very rigorous calculation, and that are some rare cases. One of the cases is such that when a circular plate is clamped along the edges. So, that is one case, a rare case, circular plate clamped along the edges and subjected to UDL throughout the plate. So, Q naught per meter square, Q naught per unit square area square is the load intensity here, and A is the radius of the circle. Okay. Now, you can see how this problem can be solved. This is proceeded like that. If I assume a deflection function, say this C equal to C is an unknown constant, C into x square by s square plus y square by s square minus 1 whole square. If I assume this as the deflection function, then it shows that it readily satisfies the boundary condition. So, what are the boundary condition? Boundary condition at the fixed these edges, fixed edges will be your slope, that is deflection is 0 and the slope, because this is a curved edges. So, I take slope with respect to normal direction del n, and this can be decomposed into Cartesian coordinate slope also, that we have seen if the angle of inclination with the original x axis is known. That derivation I have done in my earlier classes. So, these two conditions have to be satisfied at the edges, and taking this function you can see that at the boundary x square plus y square is equal to s square. So, this quantity becomes 1. So, 1 minus 1 is 0. So, deflection is satisfied. Again, if you take this derivative of that quantity with respect to x or with respect to y, this expression within the bracket will come first, and then you will take the derivative with respect to x or y, whatever may be. So, again it will be 0, because this term is again appearing in the expression of slope. So, therefore, the second condition is also satisfied. So, you have to take a quadratic term with this expression x square by s square plus y square by s square minus 1 whole square. So, this gives this expression shows that boundary conditions are satisfied at once without any difficulty for clamped edges, nobody can deny. Now, if this condition is satisfied and if I think that it is the solution of the differential equation, that it must satisfy the differential equation. So, when if I take certain function as a solution, I have to substitute it in the differential equation to see whether both sides are equal. So, that means this function or w x y now have to be substituted in this differential equation. Okay. Let us see, if I substitute this in the differential equation, del 4 w equal to q by d, which is expanded in this form del 4 w del x 4 plus 2 del 4 w del x square del y square plus del 4 w del x 4 equal to q naught by d. Q naught is the uniformly distributed load. Now, you require here to evaluate or know the derivatives up to fourth order, okay? Because the expression is given for w as c into x square plus by y square plus y square by a square minus 1 by whole square. So, you can successively obtain the derivative. Okay. So, if you obtain the derivative, del w by del x is obtained, del square w del x square by obtained, del cube by w del x cube by obtained. So, lastly we go to the fourth derivative. So, fourth derivative is 24 c by a to the power 4, it can be easily verified, and similarly we can obtain the derivative with respect to y and the cross derivative that is required for the second term, that is 2 into del to the power 4 y w divided by del x square del y square. So, that quantity is also evaluated. Now, substituting all these derivative in the differential equation, in the equation number 20, we will get this constant c. C is easily evaluated as q naught a to the power 4 64 d. So, hence the deflection surface is defined by this, c is known. So, exactly deflection surface is obtained. So, from the deflection surface now you can go for other quantities like bending moment, shear force, twisting moment, etcetera, whatever you may be, but for axisymmetrical cases there will be no twisting moment. So, bending moment you can obtain. Okay. And it can be seen that maximum deflection will occur at the center. So, substituting x is equal to 0, y is equal to 0 in this expression, expression 22, we get the maximum deflection of the plate as q naught a to the power 4 divided by 64 d. Okay. So, that is very rare cases where the solution is obtained just by assuming a suitable function which is satisfying first the boundary condition, and after imposing this into the differential equation we get the unknown constant. Okay. Now, let us see the pure bending case of a plate, that is very interesting. A interesting surface is obtained when we find out this deflection of the plate. Okay. Now, the plate is subjected to pure bending along the edges M 1 and it is a symmetrical case. It is a symmetrical case, it is shown here, but there may be an antisymmetrical case also. Okay. The moment curvature relationship is expressed, you know that moment curvature relationship is this. Okay. And since there is no twisting moment, so del square w by del x del y equal to 0. Okay. Now, equation number 24 and 25 you can see here, this is the curvature in x direction and this is the curvature in y direction. Here this is curvature in y direction, this is curvature in x direction, and these are the moment, that is applied moment M 1 and M 2 on the plate. So, solving 24 and 25 simultaneously, one can obtain this expression of curvature in x direction and expression of curvature in y direction, and twisting moment as usual we have written del square w del x del y equal to 0. Now, let us integrate this, because we are targeting this w has to be found out. So, integrating the first equation we get this. After integration of first equation with respect to x, we get del w by del x and it is x and constant of integration. Now, constant of integration here I take as a function of y, because I am doing the integration with respect to x. Okay. Then again integrating the first expression, this expression I get this expression will be x square by 2. So, x square by 2 is coming, and then f 1 y into x, and then another constant of integration which also I will take as a function of y, because I am integrating with respect to x. Okay. Similarly, integration of the second curvature equation is this equation number 28. So, integrating equation number 28 we get this, first we get this. So, here the function of x will appear, and after second integration we will get another function of x. Okay. Now, integrating the twist curvature equation twist curvature now I am writing in this way, and integration of this equation simply results. Say if I integrate this equation, first equation, this equation equal to 0, then I will get del w by del x and function of g x, function of x, because I am integrating with respect to y, and in the second case I am integrating with respect to x. So, I am getting a function of y as a constant, which means that earlier cases if you compare this, you will get f 1 y is equal to constant and g 1 x is equal to constant. So, these constants I termed as a and b, equating both the expressions for w x y. Okay. W x y we have got after twice integration of curvature in x direction and after twice integration of curvature in x direction. So, equating this we get this. Okay. So, there are some interesting conclusion will arise. You can see here in the left hand side the expressions are function of x, in the right hand side the expressions are function of y. This clearly indicates, okay, because m 1, m 2, Poisson ratio and capital D all are constant, b is a constant, a is a constant. But how a function of x can be equal to function of y? This is not possible unless both are constant. Okay. So, that is very important conclusion, and based on that we take this holds good only when both the sides are constant, and that constant I am taking at minus c. So, that means in the first equation, see this is the first equation of deflection obtained from integration of curvature in x direction, and this is the second equation of deflection obtained from curvature of this y direction. So, both are constant. So, if I add this to a constant, okay, a constant is added to a first equation and we get this. Now, these three arbitrary constant a, b, c now have to be evaluated based on the prescribed condition at the boundary, or because here boundary conditions are not specified, it is just a plate on which the moments are applied. That is, in the boundary condition we know the moments, okay. But these constants can be eliminated if we take the center of the plate as the reference point from which the deflections are measured, deflection or slopes are measured. So, if I take the origin as the reference point, then I get that at x is equal to 0, y is equal to 0, the slope and deflection will be vanished because it is a symmetrical bending. So, therefore, in that case we will get a is equal to 0, b is equal to 0, c is equal to 0. So, in that case the deflection surface is simply written just like as a function of x square and y square, okay. And the coefficient of x square you know and coefficient of y square you know here, okay. That can be arranged after arranging the multiplier, okay, in a suitable way. So, once the deflection w x y is known, other quantities in the plate can be determined, that you know the usual practice. But if I take m 1 is equal to m 2 is equal to some constant value, that means plate is bent by equal couple on all sides, okay. Then you will get interesting thing like that w x y is becoming this. So, this indicates the surface deflects in the form of a part of a sphere. So, one can find in this case the radius of curvature as r x equal to r y equal to d plus mu divided by m naught. Okay. So, the surface will look like that when m 2 by m 1 is equal to 1 and Poisson ratio is 0.3. For that I have plotted, and for different values of m 2 by m 1 ratio 1.5, 3, but all are symmetrical cases. So, symmetrical bending you are finding that curvature in one direction. Okay. So, it is a synclastic surface. Now, when there is a antisymmetric moment, then you will find the reverse curvature. So, reverse curvature is seen when the moments are not equal or not symmetrical. I should not tell it equal, magnitudes may be whatever may be, but this is not symmetrical. Okay. So, in that case m 2 by m 1 is minus 1.5, that the senses are different, and here m 2 by m 1 is minus 3. So, here you will get a reverse curvature, and therefore, this type of surface is known as anticlastic surface. If I see the pure torsion of the plate, so in that case bending moments are 0, only the torsional moment is applied, and torsional moment equation we know, this is the torsional moment equation this, and we can write this torsional moment equation as this. So, integrating above equation and using same argument as before, we can arrive W as minus m x y d into 1 minus nu. So, this is the another equation, okay, for deflection subjected deflection of a plate subjected to pure torque. So, pure moment is there. So, in that case the deflection surface will look like that. Okay. So, let us see whatever we have covered in this lecture. Let me summarize this. So, in this lecture we discussed about the analytical solution technique available for the plate equation. Then we have introduced different boundary condition in the plate, classical boundary condition, non-classical boundary conditions, plate edges simply supported, clamped, free. These are the 3 classical boundary condition. Non-classical boundary condition, edge resting on the elastic beam, then your edge resting on the elastic beam, then edge resting on the elastic spring, then edge resting on the rotational spring. In the first case the edge resting on the linear elastic spring, and in the second case the edge resting on the rotational spring. Okay. So, this type of boundary condition we have seen. Then I have focused that there are some cases where the closed form solution can be readily obtained. So, these are the rare cases, and it happens for some particular boundary condition and particular type of loading, not for all cases. Okay. Very limited cases it can be obtained. So, one of such cases is the circular plate clamped along the edges and subjected to uniformly distributed load. So, that case I have demonstrated, okay, how to find the deflection, taking a suitable deflected surface to find the unknown constant associated with the deflection function, and from that we have seen that the maximum deflection occurs as we expected at the center, and magnitude is given in terms of the radius square and this load intensity and your radius to the power 4 load intensity and this flexural stiffness of the plate. As usual in case of beam also we have seen that deflection decreases if we increase the depth of the beam. Here also in the plate equation we have seen that deflection decreases when the thickness of the plate is increased, because in the flexural rigidity of the plate the h cube term is appearing. So, there is some there is similarity with the beam and plate also. So, then we have seen that pure bending of a plate subjected to a moment at the edge moment, okay, of same sense, but of different magnitude, and then when the magnitude of the moment and sense of the moments are equal, a purely symmetrical case of equal magnitude, then we have seen that deflected surface is in the form of a is a part of a sphere, and radius of the sphere can be easily computed from this deflected surface by taking the second derivative, the curvature, and reciprocal of this will be radius of curvature. Then we have seen that for antisymmetric moment there will be reversal of curvature. So, the 2 terms I have introduced, one is synclastic surface where the curvature is in the same direction, and anticlastic curvature the bending takes in a reverse way. Okay. So, reversible curvature occurs due to antisymmetrical loading. Then we have seen the pure torsion of a plate and how it is solved from the twist equation in a very simple way, and we have demonstrated the form of the surface that is formed due to pure twisting. So, okay, thank you. Again we will meet in the next class to proceed further. Thank you.